So up until this point, you were told or you thought that you couldn't square root negative numbers. This was a problem that mathematicians ran into, one in particular, when he was trying to prove a theory. And so they needed a way to overcome this issue. So they created the imaginary unit, I, to help overcome the problem of equations that didn't have any real number solutions, because somewhere along the line you had to square root a negative. The imaginary number is defined as I, this little italicized I that you see right here, is equal to the square root of negative 1, or given that, so if I square both sides, I squared, when I square a square root, the squaring and the square root undo each other. So if I do this, I end up here with I squared equal to negative 1. So for the first time we have a value that when you square it, it gives you a negative. And it is what we call the imaginary number. So we have two properties. The first property says if r is a positive real number, then the square root of negative r is equal to I times the square root of r. For example, if we have the square root of negative 3, we can think of that as the square root of negative 1 times 3. By the product property of radicals, I can break that down into the square root of negative 1 times the square root of 3, and we've just defined above that the square root of negative 1 is equal to I. So we get I square root of 3. By property 1, then, it follows that I square root of r squared is equal to negative r. So if we take that I square root of 3 and square it, well, I squared, and then squaring the square root undoes the square root, times 3, and we defined above that I squared equals negative 1. It'll be negative 1 times 3, and we will in fact get negative 3. And the reason this is coming up now is because in the last section we talked about solving via square roots. And so sometimes we end up needing to square root a negative. Let's take a look at a couple of examples. Again, we can only solve with square roots when you have a quadratic term and a constant term. If there's a linear term, it is not set up for square roots. We only have a quadratic term and constant terms, so we're good to go. Let's isolate that quadratic term. So we'll subtract the 11, we'll have 2x squared equals negative 48. We'll divide by 2 to see that x squared equals negative 24. So now I need to square root both sides to determine what x equals. So we would get x equals plus or minus the square root of negative 24. But I gotta break that down because I can't leave a negative under my square root and I can't leave any perfect squares inside. And I know that 4 is a factor of 24. So I'm going to break negative 24 down into negative 1 times 4 times 6. So we'll have plus or minus the square root of negative 1 times the square root of 4 times the square root of 6. We'll use the product property. Okay, so the square root of 4 is 2. The square root of negative 1 is the imaginary number. And then we have our square root of 6 since it doesn't come out evenly. So those would be our two solutions to that problem. Let's try the second one. Same exact steps. Isolate the quadratic term. So take away 18 from both sides. we get negative 90 is equal to 2x squared. Then we need to square root both sides to figure out the value of x. So we'll get x equals plus or minus. Remember, you need that anytime you take a square root when you're solving an equation. The square root of negative 45. Well, I've got to break that down because I can't leave a negative under my square root. And I also know that 9 is a factor of 45. So I break negative 45 down into negative 1 times 9 times 5. So via the product rule, I can write the square root of negative 1 times the square root of 9 times the square root of 5. So the square root of 9 is 3. The square root of negative 1 is I. And then we have the square root of 5. So it's plus or minus 3i square root of 5. So when we combine real numbers with imaginary numbers, we get what is called a complex number. A complex number written in standard form is a number a plus bi where a and b are real numbers. The number a is the real part of the complex number, and the number bi is the imaginary part. If b does not equal 0, then a plus bi is an imaginary number. If a equals 0 and b does not equal 0, then a plus bi is a pure imaginary number. Two complex numbers, a plus bi and c plus di, are equal if and only if a equals c and b equals d. So in other words, corresponding parts have to be equal. For example, if x plus yi is equivalent to 5 minus 3i, then x must equal 5, and y must equal negative 3. So standard form, remember, means that your real part is first, plus or minus your imaginary part. So when they ask us to write the expression as a complex number in standard form, they just mean to combine like terms, real parts with real parts, imaginary parts with imaginary parts, and just make sure that in the end, when you write it, you put the real part first, plus or minus the imaginary part. So in example 3, we're going to combine the real numbers and combine the imaginary numbers. So 8 plus 5 gives us 13. Negative I plus 4i gives us 3i. So we have 13 plus 3i. For number 4, same idea, only it's subtraction. So we'll subtract the real parts, subtract the imaginary parts. So 7 take away 3 gives us 4. Negative 6 take away, and negative 6 is negative 6 plus 6, which is 0. So we end up with a real number. The imaginary parts drop out. Number 5, I'm going to start by distributing the negative. So 10 minus 6 minus 7i plus 4i. And now I'll combine my real parts. 10 take away 6 is 4. Negative 7i plus 4i is negative 3i. Electricity is an excellent example of where imaginary numbers are used in the real world. Circuit components such as resistors, inductors, and capacitors all oppose the flow of current. This opposition is called resistance for resistors and reactance for inductors and capacitors. A circuit's total opposition to current flow is impedance. All of these quantities are measured in ohms. So here's a chart in which they show us the different symbols used for reactance, impedance, for resistor, inductor, and capacitors. And then they give us a diagram of an alternating current source and the different things encountered. So the table shows the relationship between a component's resistance or reactance and its contribution to impedance. A series circuit is also shown with the resistance or reactance of each component labeled. The impedance for a series circuit is the sum of the impedances for the individual components. Find the impedance for the circuit shown above. So, this one is an inductor. This one is the resistor. And this one is the capacitor. So we're going to add up the impedance for each. So for the inductor, it's an imaginary number, so it's 3I. The resistor is a real number. Then the capacitor is a negative imaginary number. So if we combine like terms and write this in complex form, standard form, we get 5 minus I ohms. So next we have some practice writing these in standard form, only with multiplication and division. So number 7 shows the distributive property of monomial times a binomial. So 4I times negative 6 gives me negative 24I. 4I times an I gives me 4I squared. Well, remember that I squared by definition equals negative 1, so this is really 4 times negative 1, which is negative 4, a real number, and we should put it out front. We can't forget that the imaginary part was negative 24I. So this one is negative 4 minus 24I in standard form. The next one is a binomial times a binomial, so we'll use FOIL. We'll get negative 36 plus 63I plus 8I minus 14I squared. So we've got negative 36 plus 71I minus 14 times negative 1. So we have negative 36 plus 14 plus 71I. So we get negative 22 plus 71I when in standard form. The next section is about rationalizing the denominator, because remember your denominator must always be a whole value. You can't have negatives down there, or square roots, or imaginary numbers. So we are once again going to rationalize by multiplying by the conjugate. So I'm going to look at my denominator, and I'm going to find its conjugate, flip its middle sign, and I'm going to multiply the numerator and denominator by that. I have to use FOIL, so in the numerator I get 7 plus 28I plus 5I plus 20I squared. In the denominator, I get 1 plus 4I minus 4I minus 16I squared. So in the top, I'll have 7 plus 33I plus 20 times negative 1 over 1 minus 16 times negative 1. And so we can already see the i's dropped out of the denominator, making it rational. In the numerator, I'm going to combine the 7 with the negative 20 and get negative 13 plus 33I. Negative 16 times negative 1 is positive 16, plus the 1 is 17. So my standard form with the rationalized denominator is negative 13 plus 33I over 17. Same idea on number 10. So I'm going to multiply by the conjugate of the denominator, which is 5 plus I. So I'm going to use FOIL, multiply my first terms, my outside terms, my inside terms, and my last terms. Same in the denominator, first terms, outside terms, inside terms, and last terms. So I start simplifying the top. 15 plus 23i plus 4 times -1 over 25 minus -1. So again, you can see the i's dropped out of the denominator, making it nice and rational. In the top 15, take away 4 leaves me with 11 plus 23i over 25. Take away -1 is really 25 plus 1, so 26. So we won't do a ton with graphing complex numbers, but just so you know, you could graph them. Use a special set of axes where the x-axis is now the real number portion and the y-axis is now the imaginary portion. So we have a complex number 3 minus 2i. That means the real part is positive 3, so we would go to the right 3 units. The imaginary part is -2, so we'd drop down 2 units. And there would be our point for letter A, 3 minus 2i. The next one says -2 plus 4i, so the real part is -2, meaning I'll go to the left 2. The imaginary part is 4, so I'll go up 4. And there's my point for letter B. For letter C, it says 3i, which means the real part is 0, so I won't go left or right at all. The imaginary part is 3, so I'll go up to 3. There's my point C. For letter D, it's -4, take away 3i, so the real part is -4, so I'll go to the left 4. And then -3i, so I'll go down 3. And there's my point for letter D. We can also find the absolute value of a complex number. Recall that the absolute value of a real number is the distance from 0 on a number line. But with complex numbers, we can't just use a one-dimensional number line. There's 2 dimensions to it. There's the real part and the imaginary part. So we have to use our 2-axis system. And so to find the absolute value, we're going to bring in Pythagorean theorem. We want to know how long this distance is. So we're going to have to use Pythagorean theorem and draw the right triangle. One of the legs will be the real part, the other would be the imaginary part, and we're looking for the length of the hypotenuse. So the absolute value of a complex number, z equals a plus bi, denoted by absolute value of z, so just like as if it were a real number, is a non-negative real number defined as the absolute value of z equals the square root of a squared plus b squared. This is the distance between z and the origin on the complex plane. So let's take a look at 2 examples. If we want to find the absolute value of -4 plus 3i, Well, we can graph that on our grid above, so -4, meaning 4 units to the left in the real part, plus 3i means we go up 3 in the imaginary part, and so here's our point for number 11. And I want to know how far from there to there, so I'm going to draw straight down, straight over, and form a perfect right triangle in which I'm looking for the hypotenuse. So one leg is 3, the other leg is 4. So this absolute value, the distance from the origin, is going to equal 3 squared plus the -4 squared So the absolute value of -4 plus 3i will equal the square root of 9 plus 16, or the square root of 25, which is 5. For -3i, so the absolute value of -3i, if we plot that on our graph, -3i means that the real part is 0, so we don't go left or right. We just go down 3 points on the imaginary part. And so if we were going to calculate this distance, we could just actually count it since it's just straight. It's 3, but we can show it with the absolute value formula listed above. So the idea that it'd be 0 squared plus 3 squared, and you'd have 0 plus 9, so you'd get the square root of 9, which is 3 units. So just keep in mind that absolute value always talks about the distance from 0. It's just that with complex numbers, they're on a two-dimensional coordinate axes with real and imaginary numbers. So it's the distance from the origin. So we need the Pythagorean theorem in order to be able to calculate it. Those are the notes on complex numbers. Rewind, rewatch as needed, read your textbook. Make sure you've got a good foundation of understanding about the imaginary unit and how to use it with complex numbers.